The Sun emits radiation across the entire electromagnetic spectrum. Therefore, missions designed to study the Sun and most interplanetary spacecraft carry a suite of different instruments that study a wide range of wavelengths to gather as much information as possible. For example, ultraviolet wavelengths can probe atmospheres and magnetospheres. Near-infrared and X-rays can be used to study the mineralogical properties of chemical composition of solid surfaces, and radio wavelengths can be used to map large-scale features and surface properties. A spacecraft that makes the journey across the solar system to another planet can take close-up images of the surface as well as directly monitor its atmosphere and interaction with the particles emitted by the Sun. A spacecraft in orbit around another world can provide constant monitoring over a long period of time and view regions that cannot be seen from the Earth. A spacecraft that can land on the surface of a solar system body provides an even closer view and can study detail that is so small it cannot be viewed by an orbiter, let alone from Earth. These robotic explorers can contain a suite of experiments in which samples of rock or gases can be collected and tested directly. The ultimate next step is to bring these samples back to Earth, where they can be studied in laboratories using a multitude of techniques and in much finer detail. Exploring the solar system in this way has completely changed our view and has transformed our understanding of our nearby celestial neighborhood. Ulysses was the first mission to fly over the Sun's poles, making it possible to map the solar wind in 3D for the first time. The Solar and Heliospheric Observatory, or SOHO, pioneered techniques for looking at the solar surface and has revealed the true nature of the Sun's violent atmosphere, and as a byproduct discovered over 1,000 comets. The Cluster mission watches as the solar wind impacts and interacts with the Earth's magnetosphere, the region in which charged particles are influenced by the Earth's magnetic field. Cluster has made accurate measurements of the motion of plasma in the Earth's magnetosphere, as well as determining the shape of boundaries between the Sun and the Earth's magnetic fields. Continuing the early studies by the Soviet Venera lander series in the 1970s, Venus Express is orbiting this inhospitable planet, peering through the thick atmosphere. This mission has studied the structure and dynamics of the Venusian atmosphere and has confirmed the presence of lightning. In addition, the data that is being gathered about this harsh planet indicates that it may, to a certain extent, have been more Earth-like at some point in the past. The planet Mars has been visited by a number of spacecraft since the 1960s. Mars Express is continuing to map the surface and monitor the climate of the red planet. This orbiter, by making color, stereo, and multi-wavelength observations, has discovered new geology, climatology, a water ice reservoir, and detected traces of methane in the Martian atmosphere. After a journey of nearly 7 years, the Cassini-Huygens spacecraft, made up of NASA's Cassini orbiter and ESA's Huygens probe, became the first to enter orbit around Saturn. In early 2005, the Huygens probe successfully traveled through the atmosphere of Saturn's largest moon, Titan, and touched down on the surface. This is the only landing to have taken place in the outer solar system and the furthest from Earth. Giotto was ESA's first deep space mission and part of an international fleet that flew very close to a comet. This mission encountered the famous Halley's Comet, showing for the first time the actual shape of a comet's surface, known as the nucleus, as well as revealing the interaction of cometary material with the solar wind. Rosetta, ESA's next comet chaser, is on a 10-year journey through the solar system to encounter Comet 67P Churyumov-Gerasimenko in 2014. This spacecraft will go into orbit around the comet and deploy a small lander onto the icy nucleus.
All these European missions have made and are continuing to make important contributions to our understanding of the solar system as a whole. In a very short period of time, our understanding of the structure, composition and evolution of the solar system has increased dramatically. However, this increased depth of knowledge has generated even more questions, and further exploration is required to answer these new questions and fill in the gaps in our knowledge. For example, exactly what triggered the initial collapse of the nebula from which the Sun formed? Was it the shockwave from a nearby supernova? Did the Sun exist as a fully fledged star before the planets formed? Or did the Sun and the planets all form at the same time? All the planets in the solar system developed from the same material. But why do their atmospheres and surfaces vary so much? Comets and asteroids are material left over from the formation of the solar system. What are they made from, and could they hide clues about the origin of the solar system? Energetic particles emitted by the Sun as a solar wind spread throughout the solar system. How do planetary atmospheres and magnetospheres respond to interaction with these particles? No evidence for life, either past or present, has yet been discovered elsewhere in the solar system. So what are the conditions for the origins of life, and why did it evolve on Earth? The European missions now exploring the alien worlds of our solar system are contributing to the gathering of information scientists need to keep on piecing together the story of the solar system's past, present and future. Over a short period of time, Europe has played an important role in our quest to understand the solar system and our place within it. I'm Rebecca Barnes. Thank you for watching the Science at ESA vodcast.